Remember, this was a necessary discussion for us to understand the concept of orthogonality. So, I want you to briefly go back to our discussion where I said that any polarization can be written as the sum of two plane waves, right? And we specifically looked at two plane waves where the electric fields were linearly polarized for each of the two plane waves, and the direction of the electric field was perpendicular to each other, and I said that this forms a special basis and we call them the orthogonal basis, but that is not the only unique basis, right? So, we consider any two plane waves, right, orthogonal, and when the orthogonality condition is satisfied, we can use them as the basis to construct any polarization that we may want, right. So, the condition for orthogonality is the sum of the individual powers of the plane waves. I am going to add in the basis set. I hope it makes sense. Is equal to the total power of the composite wave. Right. So, in order to say that if you were to give me two plane waves, right, which have a certain polarization each, and if you ask me the question, can these two form a basis to represent any random polarization with this, any arbitrary polarization, the first question to ask is, will the sum of individual powers of these plane waves when combined with any phase difference between the two, right, yield the total power of the composite wave, right. So, what does this require happen? So, we are asking that half of real of. So, remember that I have two plane waves in the basis set. Let us use E1 and E2 to represent them. Remember that these fields can be linearly combined, right, and I am taking the cross product, right. So, if I were to expand this, I get E1 cross H1 star plus E1 cross H2 star plus E2 cross H1 star plus E2 cross H2 star. Okay, and if the two plane waves are said to be orthogonal, then I require that these two go to 0. This is my condition for orthogonality. Okay, so when this condition is met, I essentially have right. So I can write this as P average 1 plus P okay. So the two plane waves where the two electric field vectors for each of these plane waves were perpendicular to each other is but only one example of orthogonal plane waves. Surprisingly, there are many plane wave basis sets that are perpendicular are orthogonal to each other, right. So the reason why I took the time to explain the meaning of orthogonality is its connotation from linear algebra should not be directly implemented here, right. So the orthogonality here means something a bit more than being perpendicular than each other, right. So for example, I'll leave this as an exercise to the students who are watching this. You can show that the right circular polarization and the left circular polarization, right, form a basis set. So I can use one plane wave which has a right circular polarization and another plane wave with left circular polarization, and combine these two plane waves to get any polarization you want, right, by appropriately choosing the phase difference between these two basis plane waves. I can combine them to get you any arbitrary polarization, right. So not only is our horizontal and vertical polarization a basis set, right, we have the right circular and the left circular polarization as a basis set as well, right. And there are plenty more, right. Even elliptical polarizations can be orthogonal. Right, I can actually find two elliptical polarizations that are also orthogonal, right. So remember that the condition for orthogonality is not about something being perpendicular to something, right. So even though the notion orthogonal in English students are mostly exposed to in the context of perpendicularity, right, but here in this context orthogonal means that I can take the Poynting vector, right, of the combined wave, and it should be essentially the same as finding the Poynting vector for each of the individual waves and then adding the two, right. And this only happens when I have E1 cross H2 star, right, and E2 cross H1 star, both being 0, right. Okay.